For example now, I have oxygen and nitrogen, both of them. I don't even have to draw them out. I could draw them out, but I realize oxygen and nitrogen are part of my Hofbrinkel family. If they're part of my Hofbrinkels, they are diatomic. It means it means they are nonpolar, therefore they're held together by dispersion only. Well, why then is oxygen have a higher, they're both held together by dispersion, why does oxygen have a higher melting point than that of nitrogen? And the reason why is because oxygen is heavier. So again, we see this oxygen weighs in at 32, nitrogen weighs in at 28. So as we increase the molar mass, we increase the actual boiling point. So molar mass of oxygen is greater than that of nitrogen. Now part B is why is NO, nitrogen monoxide, greater than have a higher boiling point than nitrogen and oxygen? Well, again, we already know nitrogen and oxygen are dispersion, so we look at NO. Now I don't even have to know who wins or who loses. All I know is I have two different elements. They're going to have two different electronegativities. Someone's going to gain and someone's going to lose. Someone's going to become positive, someone's going to become negative. So if I gain negative or I lose positive. So I have two charges. I have a dipole. So right away I know, oh, dipole is stronger than dispersion only. So if I look at this, it's going to be lopsided. It is lopsided. My oxygen is going to be partially negative. My nitrogen is my partially positive. So in NO binds with another NO, it's going to be a dipole bound to a dipole. Now, like I told you, we're filling the bucket. And dispersion is at the bottom of our bucket, then dipole is in the middle, and hydrogen is at the top of our bucket. So we must include dispersion. Once again, the strength of the intermolecular forces increase the actual boiling point. Next we're going to take a look at I want to know the types of the intermolecular forces. And I just have to look at hydrogen. Right away I know, oh yeah, it's diatomic, it's in the Hofbrinkel family, therefore it's nonpolar. All nonpolars are held together by dispersion only. I didn't have to draw it out. Next one, CCl4. Well, carbon's in group 14, loves 4 bonds. Oh, there's my 4 X's. It's an AX4. It's an ideal geometry. The X's are the same. All ideal geometries, as long as the X's are the same, are nonpolar, therefore held together by dispersion only. My next one, OCS. I'm looking at the oxygen and the sulfur, and so I realize someone's going to be pulling more and someone's going to be pulling less. So someone's going to win, someone's going to lose. I'm going to create a partial positive and a partial negative. Therefore, I create a dipole. So again, I include dispersion along with that. Next, NH3. When I draw this one out, NH3, I realize, oh, this is a dipole. Because again, the movement above my nitrogen never cancels, so it's going above my nitrogen will be a negative, and by my hydrogens will be positive. But I realize here in this situation that, oh, you know what? Nitrogen or hydrogen is also bound with bond. So I get my fluorine. And I get my hydrogen bond there. So dispersion, dipole, hydrogen bond. And the last one, it is an ionic compound, so right away I know ion-ion. Now I include dispersion, because dispersion is involved with everything. Remember ionic compounds, even when we were 80% ionic, we were still 20% covalent. So dispersion is going to be involved there. So when we look from strongest to increasing, we're going to go from weakest. First of all, I look at my two dispersions, H2 and Cl4. Which one's stronger? Well, CCl4 is, because it's going to be heavier. So my hydrogen is my weakest, so my CCl4. Then I'm going to go to my dipole. Then I go to my hydrogen, which is ammonia, and then my calcium chloride, which is anionic, and that'd be the strongest. Next, I want to know which one of these is going to have hydrogen bond. Now remember, hydrogen has to come in contact with Fon. So I look at the first one and realize, well, Fon's not even present. So no hydrogen bonds can be present there. I look at my second one. What I do is I keep it in order. I put the carbon, oxygen surrounded with hydrogens, and I realize, oh wow, again, in this situation, oxygen does come in contact with oxygen, or hydrogen does come in contact with oxygen within the compound. Therefore, I'm safe to assume that they will be in contact between. When they're between, we call it a hydrogen bond, so yes, they'll be present. The last one, I put my two carbons and my oxygen in the middle. I have hydrogens all the way around. I see the hydrogen never comes in contact with actually oxygen. Therefore, if they don't come in contact within the compound, they're not going to be present between. Therefore, I would say there is no hydrogen bonds there. Moving on. And now explaining these statements. If I look at this, I want to explain this in terms of intermolecular forces. So the first statement says that ICl has a higher melting point than Br2. Well, Br2 is a Hofbrinkel. It's nonpolar, held together by dispersion only. I look at iodine and chlorine. They're two different elements. They're going to have two different electronegativities. Someone's going to win, someone's going to lose. Someone's going to be partially negative, someone's going to be partially positive. I have two poles. I have a dipole. That's why then it has a higher boiling point. I look at ICl. It says ICl has a higher melting point than bromine. Now bromine, again, is a Hofbrinkel, therefore it is nonpolar, held together by dispersion only. But I look at ICl and I realize that I have two different elements, iodine and chlorine. Iodine and chlorine, someone's going to win, someone's going to lose. They're going to have different electronegativities. I don't really care who it is, but I know this. And when someone loses and someone gains becomes partially negative, someone loses partially positive. I have two poles, I have a dipole. That's why my ICl has a stronger bond than my bromine and a higher boiling point. Moving on, C2H6, which is ethane, has a higher boiling point than CH4, which is methane. Well, I see both these are carbon-hydrogen bonds, therefore both of them are hydrocarbons. All hydrocarbons are non-polar, held together by dispersion only. So then I can think, well, they're held together by dispersion. Why is it that ethane is stronger? Well, because it has a higher molar mass, right? It's heavier. And so I have two carbons versus one in methane. So it's heavier, therefore I increase the molar mass or molecular weight, therefore I increase the actual boiling point. Letter C. I have H2O2, which is hydrogen peroxide, and then I has a higher boiling point than my C2H6. So the P is left out in boiling point, but it has C2H6. When I look at C2H6, I realize, oh, that's a carbon hydrogen, that's a hydrocarbon. All hydrocarbons are non-polar, held together by dispersion only. And then I look at my H2O2 and I realize, oh, with that bond, this actually hydrogen does come in contact with oxygen within, therefore it's going to be present between. With that, I get up to a hydrogen bond. So I'm actually filled the bucket all the way. So at the bottom of the bucket, filled dispersion, went past the midway point in my bucket, which is dipole-dipole, and I got all the way up to hydrogen. All three of these are involved in the bonding process, but you top out at the strongest one, which is hydrogen. When I look at my hydrocarbon, it just filled up the dispersion. It barely filled the bucket. Looking at letter D. Letter D, now I have an ethanol. When you see OH, that's an alcohol. So I realized with that one, oh, alcohol, that means hydrogen and oxygen are going to come in contact. There's a hydrogen bond there. But I look at sodium fluoride. Well, sodium's in column 1, fluoride's in column 17. I know it's an ionic compound, therefore ion-ion. So again, that's why on part D, that's why the sodium fluoride has a higher boiling point than my ethanol. It's ion-ion. My last one, letter D. I have an alcohol in OH as a hydrogen bond, has a higher boiling point, so my ethanol has a higher boiling point than my butane. Or I look at butane. Butane is strictly carbon and hydrogen, therefore it is a hydrocarbon. All hydrocarbons are non-polar, held together by dispersion only, whereas I see my ethanol also gets up to a hydrogen bond, so again, it fills the bucket versus my butane. Therefore, again, that explains why my ethanol has a higher boiling point, has stronger intermolecular forces.